Hey there, welcome back to Foolish Engineer videos. Today we are diving into the fascinating world of low-side bidirectional current sensing circuits. These circuits are unsung heroes of many electronic applications, and by the end of it, you'll see why. One of the key reasons I started this YouTube channel is to bridge the gap between outdated Indian education system and actual skills needed in the industry. I'm excited to share that this video is sponsored by Altium. If you are an electronics student in India, you can get Altium Designer and Altium 365 for free under its Altium Student Lab program. It is an advanced electronics hardware design platform. It's a fantastic way to enhance your skill and increase your chances of landing a job in core electronics companies. And with its best feature, Altium 365, you can upload projects to the cloud, manage libraries, collaborate, and review with your team. It supports all CAD files, making an electronics design faster and easier. Just use your university email to get started. Plus, you'll receive a student license, a PCB design course, and a certificate recognized by top Indian industries. You also get a free access to Power Analyzer by Keysight. I have personally used Altium Designer since the start of my electronics journey, and I really recommend it. So don't miss this chance. You can get started with Altium 365 by clicking the link in the description. First things first, what exactly is low-side bidirectional current sensing circuit? Imagine you are a traffic cop, monitoring the flow of cars on a busy street. You need to know not only how many cars are passing by, but also in which direction. That's essentially what this circuit does, but with electrical current. In technical terms, it measures the current flowing through a load by monitoring the voltage across a low value resistor, called a shunt resistor, placed on the low side. This setup helps us detect the current flow in both directions. So it is called as bidirectional. Now, let's break down the design of our low-side bidirectional current sensing circuit. For that, we'll need few key components. First is shunt resistor, two operational amplifiers, and some precision resistors to ensure accuracy. The shunt resistor is crucial because it creates a small voltage drop proportional to the current flowing through it. This voltage drop is then amplified by the operational amplifiers to give us a readable output. Here is how it works. When current flows through the shunt resistor, it creates a voltage drop. This drop is picked up by the first op-amp U1, which is configured as a differential amplifier. It amplifies the voltage difference between input terminals. The resistors R1, R2, R3 and R4 configure the gain of this amplifier. The second op-amp U2 sets and provides a stable voltage reference. So the U2 will act as a buffer. The reference voltage will denote 0 ampere current. The output voltage from U1 indicates the current direction and magnitude. If the output voltage is greater than this reference, it indicates positive current. If the output voltage is less than reference voltage, it indicates negative current. And if output voltage is equal to the reference voltage, it indicates zero current. So using this circuit, we can determine the current in both directions with just a single supply. These low-side bidirectional current sensing circuits are everywhere. They are widely used in battery management systems, which monitor charging and discharging currents to ensure battery health, or power supplies to keep the track of current flow to prevent overloading and ensure efficient power distribution. And in motor control, they help to control the speed and direction of the motor. Think of these circuits as the heart rate monitors for electronics, constantly keeping an eye on the flow of electrical energy. Now, let's take an example and see how we can design such a circuit, where the current in the circuit is in the range from -1 ampere to 1 ampere DC, and we need to provide this in a voltage signal from 0 to 3.3 volts. So we'll keep some margin and design a circuit such that 0 ampere current will be denoted by 110 millivolts and 1 ampere current will give us 3.19 volts out of the current sensing circuit. And for this circuit, we provide VCC supply of 3.3 volts, which is sufficient, and we need to connect VEE pin to ground. To get the design of the right circuit, we need to keep some things in check. First is to maintain shunt resistor value as per current. Then ensure peripheral resistors R3 should be equal to R1 and R4 should be equal to R2 to minimize the errors. And we should use precision resistors for R1, R2, R3 and R4 to get more accuracy. As we saw, this is the circuit diagram. First is to select the shunt resistor. To determine the value of this resistor, we need to finalize how much voltage drop is sufficient to read for the amplifier. Here, 100 millivolts for 1 ampere is sufficient. So just by using simple Ohm's law, we get the shunt resistor value, which is 100 milliohms. We should select a bulky resistor so that it can also handle the power dissipation across it. Now, we need to determine the value of their reference, which will be around 1.65 volts considering 3.3 volt VCC. This reference is mid-supply, so we'll keep R5 and R6 of the same value, which is around 10 kilo ohms. Now, we should set the difference amplifier gain based on the op-amp output swing. The op-amp output can swing from 100 millivolts to 3.2 volt with 3.3 volt supply. So we can calculate the required gain using this formula. So the required gain comes out as 15.5. Now we have to select the values of R1, R2, R3 and R4. We just saw earlier that the value of R3 should be equal to R1 and R4 equal to R2. So we will choose R1 and R3 as 1.3 kilo ohms. Considering the input signal coming from the shunt, the value of this resistor should not be too high or too low. We already know the required gain and value of R1 and R3, so we can easily calculate the values of R2 and R4, which comes out as 20.15K, but we'll use standard value of 20K. The design of U1 is actually a differential amplifier. We have already seen the details of this circuit in this video. You can check more about by clicking on this card. Finally, we'll select op-amp OPA 313 from Texas Instruments for this circuit. Well, we can use simulation tools like TINA from Texas Instruments to simulate this circuit as well. You can check the description for more details. And that's all for now. You have just unlocked the secrets of low-side bidirectional current sensing circuits. These little circuits are important in mainly electronic applications. Don't forget to check the description for references and simulation files. If you found this video useful, hit that subscribe button as well. And stay tuned for more engaging content.